Okay, and then now we can understand this beta of u. So probability of this type 2 error, but it's dependent on mu. But still, this region is fixed and solely determined by our null hypothesis. And this region is actually acceptance region, right? Acceptance region. And then we are computing this probability of type 2 error based on the alternative hypothesis distribution. Okay, and then we have to manipulate this guy a little bit more. So this x bar is following this distribution. Where this mean value is certainly different from mu 0. So mu 0 is something like 175, and this guy was something like 185. Okay, so your sample mean was actually following this particular distribution, but your test statistic is centered at 175, right? And so you have to manipulate this guy a little bit, and then in order to introduce this mu, and then we put minus mu, and then we have this minus this part. Okay, and then then this this part, okay, except for the middle one, that will now become the standard normal random variable, right? So that way we can change it with the z. And then the remaining part will be here. And then we have this, and then we put this into the other side, and that way the z will become here. And then the probability will be represented by this. So what is this guy? The sigma. So it's like cumulative probability function, right? So it's like, so this value plus some other value, this same value minus some other value. So it's like, when having this distribution, in this case, we first compute the probability of this part, okay, minus the probability of this part. Okay, so this part will correspond to this term, and this entire part will correspond to this term. Okay, and then let's try to understand just a little bit more on this equation. So again, your distribution is following, having the center or the mean value at 185, right? And then your acceptance region was centered at 175, right? And then you have to consider this difference, right? And this difference was put here, even though we have this part, but that is due to the normalization kind of effect. And then minus and plus this z values. Okay. So that way, the point is beta is a function of mu. Okay. And if when mu 0 was 0, and if mu was 1 or 2 or 3 and so on, when the alternative hypothesis is true, of course. In that case, we can compute this corresponding beta, or the probability of type 2 error, and then it will have this kind of, this thing. So that is called a operating curve. Operating characteristic curve. And also, has anyone heard about this ROC curve? It's I think it's the same thing, but it's a receiver operating characteristic curve. And, anyone heard about it? Okay, so yeah, this one is. What about this precision recall curve? Precision recall curve. No one? Okay. So these are the evaluation metric, frequently used in the machine learning. And so, at some point, you should be able to study these. Maybe in an year or two. Okay, and then this guy, 1 minus beta was corresponding to making the correct decision. Making the correct decision when the alternative hypothesis was true. Okay, so your method is indeed better than the other, and then your sample, fortunately, your kind of acceptance region, your sample mean was fortunately outside of this acceptance region. Okay, so this is the this is also this correct cases. And then this one is of course 1 minus beta, assuming that this H1 is true. And in this case, it's called a power, and also it's called a power function in terms of the mu. Okay. So this is one important term, power of test. So you are performing the hypothesis testing, and then what is the power of your test? Okay. So your power is some probability value, and this probability is corresponding to the case where your alternative hypothesis is true, and then the probability of correctly making the decision. Making the correct decision. Okay, so again, your method is indeed better, and then your statistic is saying, your method is better as well. So that is called this power of test. And so again, if mu is close to mu0, in that case, your power will decrease, right? So which means you will have a smaller and smaller probability of making the correct decision, unfortunately. Okay, and then similar to like a two-sided test and a one-sided test, and then we can one-sided confidence interval. We can think of this a one-sided test, and then the test is having these two hypotheses: is mu being mu0, and the alternative one is mu being greater than mu0. Okay, so this is a kind of a more meaningful situation. Like our method is indeed better than the existing method. Okay, so in this case, what if mu was mu0? So it is not contained in any of these two hypotheses, right? So in this situation, we just we assume that this guy is included in the H0 or the null hypothesis. So even though we write it, but if you want to show that your method is working better, then your null hypothesis is containing the two situations where your method has the exact same mean as the exact same performance as the existing method, and also your method is actually worse than the existing method. Okay, so those two situations are included in this null hypothesis, because that is those situations that we do not want, right? Okay, and then the null hypothesis having this mean 175, and then in this case, what will be the critical region, and what will be our sample mean and their region for acceptance and rejection, and that will correspond to like this. The acceptance region will be, so we have a critical value which works as a threshold, and then this guy is satisfying this, and then this guy will be acceptance region, and the rejection or critical region will be x bar being greater than c, or maybe equal to c, right? So that way we can easily decide the inequality kind of direction. Okay, and then so these are the acceptance region, and these are the rejection region or critical region, right? So we have to put our type 1 error probability of 5% into that cyan colored part. So similar to like from two-sided to one-sided interval estimate, in this one-sided test, we put 5% of the probability or alpha value of the probability into this one side. Okay, so that way we see z of an alpha instead of z of alpha over 2, right? So overall, we will accept this guy being less than this value and reject the null hypothesis when having this equation being true. So any questions so far? Okay, and then the example will be really trivial, so you should be able to follow it easily. But let's think about this kind of p-value. Okay, p-value. So your null hypothesis was the American people's average height. The true mean was 175. Okay, and then the alternative one is actually the mean value is greater than 175. So we consider this a one-sided hypothesis. Okay, so in that case, the critical region is shown to be like this, right? Where we have some threshold value c, which is called critical value. Okay, and then let's think of the p-value. So similar to having 5% probability for this region, and then what will be the p-value when your x bar was shown to be like this? So in this case, it looks like I want to point out the direction of computing the p-value. Okay, so in this case, it can be like maybe 10%, for example. Okay, so that will be our p-value, and this p-value is greater than the allowed probability of type 1 error of 5%. So in that case, we cannot reject the null hypothesis, right? Okay, and then now let's think of this situation. So interestingly, or like a little bit counterintuitively, sample mean. So we expected at least equal or greater than the 175 for the sample mean of American people's height. But it happened that suppose we obtained the x bar as maybe 170. So it's quite opposite kind of situation. And then what will be the p-value in this case? So we have 170 here. And then should we consider this probability or this probability? Yep, the direction is not changing. Okay, so the p-value is this part. Okay, so whether some value is more extreme or less extreme, or a rarer value or kind of more commonly observed value, so the thing that decides kind of this aspect is your hypothesis, your alternative hypothesis. Your alternative hypothesis is saying that this mu is greater than the given mu value, right? So we have to consider the right part. So in this case, the p-value will be something like 0.7. So it's really a weird situation. Okay? So in that case, we will certainly like not reject the null hypothesis. Is of course, and then it's like kind of this situation. So yeah, it's the situation is, so you expected your method works better than the existing one, but your observation was actually shown to be worse than the other one. Okay. Anyways, so please don't get confused on how to compute this p-value. Okay, so the direction will not change. It's solely or entirely determined by your hypothesis. Okay, so that was one example of this one-sided test, and then we can consider the opposite case, still corresponding to the one-sided test. So mu is mu 0, and then the other one is mu is actually less than mu 0. So it can be viewed as like a defect rate of a particular product, manufactured by two different factories. Okay, so in that case, you can easily understand the rest of the story corresponding to this the other one-sided test cases. Okay, so these are the summary. So what is this TS? What is TS? Is a test statistic, right? And then this one is like the sample mean divided by sigma over n, right? So that follows Z, right? So in this case we reject it, and then if it is a bigger or like a smaller, we reject it for each case of these one-sided tests. And then just like how we extended this known variance cases into unknown variance cases, we also extend or move to a little bit more difficult situation where we do not know the variance, right? In that case, the story will be story is almost the same. Story is almost the same. So using this, okay. So we will use this as our test statistic, right? And then we replace this guy as our sample standard deviation, right? How is it defined? It is like this, right? X minus x bar squared xi, right? So this was our sample variance, and square root of it is sample deviation. So we replace this guy in the place of this sigma. In that case, this distribution will change into what? T distribution. And then what is the degree of freedom? Degree of freedom will be n minus 1, right? And then we can consider this alpha value. And if it's a two-sided test of having mu being equal to mu 0, and the other one is simply it is not equal. So it is corresponding to two-sided test. And then if it is like this, and then it's a one-sided test, it's just simply changing the distribution from standard normal random variable into this t distribution. So as we can see, we have this divided by s, divided over square root n, and then we will use this t, right? And then the threshold will be alpha over 2 in the case of two-sided test, and alpha in the case of one-sided test, and then the degree of freedom will be n minus 1. Okay, and then let's consider this p-value. Yeah, p-value. Then this guy is following this t distribution, or random variable following the t distribution, and degree of freedom is n minus 1. And then what is this guy? This guy is the observed value, computed from our sample mean and the sample variance, right? So in the previous case of computing the p-value, we ignored the alpha value, but we used this actually observed sample mean value. And then what was the corresponding probability? Matching this as a threshold in this distribution, right? So this threshold value will be obtained, and then we have to compute or obtain the probability corresponding to that region, right? So that's how we computed this p-value, right? And so in this example, let's see. Yeah, we have this t distribution, and then we found that our sample statistic, computed based on sample mean and the sample variance in this manner, was shown to be like this value. So this value is this small t value. And then what is the p-value? In the case of two-sided test, we compute this probability, right? Yep. So that will be our p-value, and it is actually like this probability times 2, because it is a symmetric distribution. Okay, so that is it for now. And then let me quickly check the attendance.